All right, guys, thank you for joining today. This is going to be 5.3, where we're going to talk about conditional probability and independence. We are going to have 2 days to do this. And so we're probably just going to get up to independence, and then we'll do that next time, okay? But overall, these are the things we're going to talk about: calculate and interpret conditional probabilities, using the general multiplication rule to calculate probabilities, doing a lot with tree diagrams to model and figure out the probabilities. And then next time we'll talk about independence, how to determine if two events are independent, and computing those probabilities. All right, so now I want to, when we're introducing the idea of conditional probability, I want to go back to an example we saw back in chapter 1, which was which was the Titanic. So Titanic, tragic event where that awesome cruise ship that was supposed to be unsinkable sank. Now, what if I just looked at all the passengers, not including crew, those who were like passengers? There was 1,207. How would I compute the probability that someone, if we were to randomly choose a passenger, what's the probability that they survive? Someone unmute and explain how we would figure that out. If you don't unmute, then I'm just going to tell Casey Nash to do it.
No.
Casey, someone's.
Wanted to get the total number of the survivors, which is 442, and then that's over the total number of people.
Thank you, Allie. Yes, and Casey, thanks you as well. Casey, you're next up. To repeat the question, so it said, what's the probability that if we randomly chose a passenger, that they survive? And yes, Allie, thank you. So I would come down here and I'd say, well, if I look at the total amount of people who survived, there was 442 out of that 1207. So I would say, let's take the 442 out of 1207, and I'm going to get out my calculator here, and I'm going to plug that in. And I get there's a 0.37. In other words, there's a 37% chance that they survive. Ooh, that's scary, right? I don't like those odds. Now, what if we change this? What if we said, instead of just randomly selecting passenger, let's assume that we knew something else about them. If we were to look at their different classes, would being in a different class change that? Was there an association between the class and the survival rate? What do you guys think? So what if you've seen the movie Titanic, it basically portrays that all the rich people got off on the lifeboats, right? And maybe that's partially true or not. But let's look at, if I were to compare, just look at the first class people. If we know that someone was in first class, how would we calculate their survival rate? Would it be the same idea? Would it be 197 out of 1207? And Casey, this is where you come in. You'd say, no, Solberg, how would you figure out the first class survival rate?
It would be those survived out of the total in first class. So it'd be 197 out of 319.
Awesome. So then I do 197 out of 319. And so when I put that in my calculator, I'm going to get that was 62%. So much better odds that they survive. Now, let's compare that to third class. I'm going to have Ashley, how would I figure out the third class survival rate?
You would take the total third class and divide it by the ones who survived. So that would be 151 out of 627.
And that's going to be lower than our total. That one, when I put that in, that's only 24%. So the question here was, did a passenger's class affect their survival rate? And we would say, yeah, definitely. Overall, we found it was 37%, like in general for everyone. But if I were to look specifically at those classes, we saw all sorts of different ones that were higher or lower. Now that's our introduction to conditional probability. So what is conditional probability? The probability we assign to an event can change if we know that some other event has occurred. This idea is the key of many applications of probability. When we are trying to find the probability that one event will happen under the condition that some other event is already known to have occurred, we are trying to determine conditional probability. So I think our Titanic example was a great introduction to this, because if we know more information, like given that they were in first class, would their survival rate change? And yes, that's what we saw, okay? All right, so keep reading here. The probability that one event happens given that another event is already known to have happened is called conditional probability. So the condition is that another event has already happened. And we think, does that change the probability? Suppose we know that event A has happened, then the probability that event B happens given that event A has happened is denoted by P of B. And then we see this vertical line here. That means given that, or under condition that A has happened. So if I were to go back and look at this, okay, so I could rewrite our probabilities, and I'm sorry, my handwriting when I use PowerPoint is even worse than normal. But if I just wanted to figure out the probability that they survive, so I'm just going to do an S for survive, okay, then that was 62%, or what was that? That was 37%, or 0.37. But if I wanted to figure out the probability that they survived given that they were in first class, that's what we found to be 62%. So the given that, it's a condition that it's an event that's already happened. They were in that class and it changed the probability. All right? So that's what we're going to be talking about a lot, is conditional probability. Now, these are your two formulas. And I'm going to show you how to use these, but then how also to do it without using the formulas. By the way, you do get a formula sheet on the AP Stats test. I'm going to post that on Canvas here soon. And this formula is given on that. So you don't have to memorize it, but you do need to know what it means. So if we see this vertical line A given B, we can calculate this by taking the probability of A. Now, someone tell me, what does that symbol right here mean? Someone unmute and tell me what that means.
And.
Yes, Casey Nash, and which is our intersection if we're looking at the Venn diagram. So we look at, if we want to find the probability of A given B, then we look at the probability of A and B, and we divide it by the probability of B. And we're going to use this formula as the last example. We're going to talk about false positives. And it's actually pretty interesting stuff. Now, to introduce it, let's talk about maybe more general one. Now, I'm going to try to, let's see if this works. I'm going to try to display this now so we can see the animations a little better, but I hope it still works out here. Okay. Here is an example. If you wanted to follow along on page 314 in your book, actually, I think that page number is wrong. Okay, well, let me just explain it because I messed up on the page number there. If we're looking at this school, okay, so there's this college that has different schools in it. It's got a liberal arts school, it's got an engineering and physical sciences school, and then it's got a health and human services school. So it's like different majors, basically, in this college. And what we're looking at is the students' grades there. And A is going to be that they got A's. B is going to be the number of B's that were given by those schools, and below B. So those are all the different grades that someone could, that they got at this college with these different schools in like a specific semester, okay? Now, we have two events here. We have E. The grade comes from an EPS course. EPS is engineering and physical science. And L is a grade is lower than a B. So if we want to figure out, find the probability of L, that's just a probability that the grade is lower than B. Kind of like what we did with the Titanic, that really isn't related to any of the schools. So we just look at the totals And we're going to say, all right, well, first off, if we're looking at grade is lower than B, how many grades were lower than a B? And that was 3,656 out of our grand total of 10,000 grades given. So approximately 36% of the grades that were given for that semester, whatever, is about 36%. About 36% were lower than a B. All right. So there was no condition given there. It was just saying, hey, how many grades were lower than a B? Now, if we're looking at find probability of E given L, let's think of what that means. That means find the probability that the grade came from EPS, meaning engineering physical science, given that it was lower than a B. So now what we're going to do here is we're going to look at the given that. So this is the condition. And so we're going to highlight the L column, okay? So we're going to be looking at given that it, hold on one second, that seemed almost a little backwards to me. Find the probability of EPS given that it was lower than a B. Okay, yes, okay, so we're highlighting the below the B, which is right here, but we're only looking at the EPS, which was the 800. Sorry, the highlight from the previous one was throwing me off. So I would take, just looking in this column, we're looking at 800 out of the grades that were below a B, which was 3656. All right, so kind of like with the Titanic example, we're limiting our focus to just one row or one column. Now, is the probability of E given L the same as probability of L given E? And it's not. E given L was we are focusing on the lower than a B, and we just looked at what's probability it's from EPS, which is that one. Now we're saying what's a probability it's lower than a B given it's from EPS. So we're going to highlight the EPS here and look at its total, which was 1,600. And then we're going to say how many Fs, or sorry, not Fs, how many below B were there, and that was 800 out of 1,600, so about 50%. So you can see that these two are not the same. They're different because you're focusing on different columns, focusing on different rows. So that's an example of how you do that with a two-way table, which I feel like you guys got that down basically already from the Titanic example. Do you have any questions on that before you try one on your own? No? Okay, well then what we're going to do is we're going to go back to an example we saw last time, which was who owns a home. So we're looking at 500 people. We randomly selected them and asked them two questions. We said, do you own a home? And did you graduate high school? And they went into these categories here, and it's got the totals included. So what I want you to do now is to take a second, and I want you to try to write this out. So number one, if we know that a person owns a home, what is the probability the person that is a high school graduate? Number two is opposite. If we know the person is a high school graduate, what is the probability the person owns a home? So I'm going to give you 30 seconds to kind of just try to set this up, and let's see how they're different. So 30 seconds, go. Oh, go back. All right, that was a quick 30, but I'm going to pause. Lillian, will you help me on number one? On number one, what is the given that? What is the condition?
If you own a home.
All right, so the person owns a home. So I'm going to put an O for owns a home, okay? And what are we trying to find out? The probability that they graduated. So I'd put it like that. The probability they graduated given they own a home. How did you figure that out, Lillian?
So first you would look at the graduate column, and then you find which one is the homeowner. So that's 221. And then out of the total of the column is 310.
All right, now the 221, you're right there. But if it's given that they're a homeowner, then what that means is we're actually going to be looking at the homeowner row here. So given that they're a homeowner, means we're looking right here. So your total, instead of doing the 310, you're going to do the 340. Does that make sense?
Yeah.
It's given that they're a homeowner. So great. So we got the 221, thank you. And then we'll do out of the 340. And then, so I'll do 221 out of 340 is 65%. So the probability that they are a graduate, given they're a homeowner, is about 65%. Cool. Thanks, Lillian. I'm going to ask Joseph to help me on this next one. What's the given that for this next one, Joseph?
Okay, so if we know the person is a high school graduate. So we're gonna go to the high school graduate column, and then our total thing is gonna be 310, and then what we're looking for is a homeowner, so it's gonna be 221 out of 310, and then we solve for the percentage or whatever.
Awesome. So I'm going to be taking, so this one's the opposite, pretty probability that they're a homeowner given they graduated. So notice Joseph was saying we need to highlight the graduated because that's the given then. So we're going to take the 221 out of 310, and I'll put that in my calculator, and I get that that's 71% or 0.71.
Mm-hmm.
So we're going to get different probabilities depending on what the condition is, depending on what the given is, okay? All right, so that's how we're looking at that, okay, so far. Do you have any questions on that?
All good here.
All good, all right. If you guys do have questions, what I want you to do is just kind of like unmute yourself and just start talking and I'll hear you. And you might think that sounds rude, but it's not. I don't see the chat as well when I'm in sharing my screen. All right, so then let's get over to what's called the general multiplication rule. If we're trying to solve for the probability of A, and as Casey told us, that's and B, right? Probability of A and B, then we're going to find the probability of A and the time and multiply that by the probability of B given that A happened. Now this is our rule whether or not we know that the events are independent or not. We can use this for any two events, okay? And we're going to do a couple of examples so that this makes sense, all right? Let's start out with a super easy example. And it's going to be drawing two hearts, okay? Now let me go back here in case people were writing that down. But if I want to find the probability of two events happening, then what I do is I take the probability of A happening and I times it by the probability of B happening given that A happened. All right, so we're going to play a game. I've got a deck of cards. Now, making sure we're all on the same page, in a standard deck of cards, how many cards are there? Someone unmute and tell me about it. What was that?
Isn't it 52?
There is 52. Good job. There are 4 suits. Who can tell me what the 4 suits are?
Spades, clubs, hearts, and diamonds.
Good job. All right. So now that means there's going to be, what's the probability of drawing a heart?
1 out of 4.
Yeah. And that's the reduced because there's 1 out of 4. But if I'm looking at the total, how many total hearts are there in a deck of cards?
Is it 13 out of 52?
It is. Thank you. All right. So here's the thing. Let's say we're playing a game, and the game is if you draw a heart, then you get a piece of candy. And I would normally do this, but since we're in a video and since we're in a pandemic, it didn't work out. But anyway, I'm going to go around the class, and let's say I go to Casey Nash and I say, hey, I want you to draw a heart. What is the probability that he is going to draw a heart? And you just told me it would be 13 out of 52. Now, Casey, you're going to say stop. And I'm drawing cards and you say stop.
Stop.
You got this card. Oh, it was a diamond.
Oh.
Okay, now I'm going to take away that diamond, okay? So that diamond is out of the deck. All right, so now I'm going to go to Jordan. And Jordan, we want to figure out what is the probability of you drawing a heart given that Casey Nash just drew a diamond.
Wouldn't that be like 13 out of like 51? Because like one card is out.
There you go. That's perfect. Okay, so there's still 13 hearts in the deck, but now the total has gone down by 51. Oh, or gone down by 1 to 51. So I'm going to start shuffling through. Jordan, you tell me when.
Stop.
Oh, you got a club. Okay.
Curses.
All right, so now I'm going to go down to Brandon. Brandon, you still want a heart, but what's the probability that you would get a heart given that Casey drew a diamond and that Jordan drew a club?
Would it just be 13 over 50?
Yeah, it just went down by 1, right? And let's just see how you do. So I'm going to be shuffling through and you tell me when.
Stop.
Hey, you got a heart. Good job,
Hey.
Brandon. You won. Okay, now the idea behind this is that the probabilities were affected by the past outcomes because we were taking the cards out, right? Now I'm gonna kind of come in here and let's see. Will this let me erase what I was doing? Yeah. So what would be the probability that I would get 2 hearts in a row? Okay. So let me get back to my pen here. I want to figure out what is a probability that I'm going to get hearts on my first draw and hearts on my second draw. Well, according to that formula we saw on this other page here, right? It's going to be the probability of hearts the first draw times the probability of hearts on the second draw, given that we got hearts on the first draw. So let's write that out here, okay? So this is, so we're just going to say, well, what's the probability of getting hearts on the first draw? And then we're going to times that by the probability that we would get hearts on the second draw, given that we got hearts on the first draw. Does that make sense how we're figuring that out?
Yeah.
Okay, so guys, what is the probability we get hearts on the first draw? You said that was 13 out of 52. I've got 52 cards in there, 13 are hearts, so that's a probability you get hearts on the first one. Now, let's assume that we did get hearts on the first draw. Then what's the probability you would get hearts on the second draw, given that you drew the heart on the first one?
12 out of 51?
Good job. So now what I'm going to do is I'm going to put that in my calculator. I'm going to do 13 out of 52, which is 1/4, and we're going to times that by 12 out of 51, and I get 0.0588. So that means statistically in the long term, if we were to do this process over and over again, in about 6% of the times we did it, we would see that we drew hearts twice in a row. Does that make sense how you would use this formula to figure out the probability of A and B? That was just kind of a simple example. I hope that makes sense. If it doesn't, please stop me so I can re-explain it. Okay, then I'm going to keep going. Now, this was an easy example, but when we're looking at a little more complicated ones, we're going to make tree diagrams. And tree diagrams are going to be your best friend this section, okay? And really, in any time you're doing probability and there's multiple outcomes, tree diagrams help a lot. So let's just look at an easy example, kind of like what we're doing, but this time let's do it with flipping a coin. So when I'm flipping a coin, my two outcomes are I can get heads or I can get tails. And what's the probability of either? It's 50-50, right? Now, if we're looking at what are all the outcomes of flipping a head or flipping a coin, I can get heads or I can get tails. And the probability didn't change, all right? So I'm going to flip the coin twice and see what we get. So if I got heads or tails, well, then on the second one, if I got heads, I could get heads again or I could get tails, and the probabilities didn't change. Down here, if I got tails the first time, I could flip again and get heads and tails again. So now, if I wanted to see what's a probability of getting heads twice, so it'd be heads on the first time and heads on the second time, this probability here, this is going to be the probability we get heads the first time. This probability is the heads we get the second time, given that the first time I got heads. Now notice these probabilities were the same. And that's going to tie into independence because we've talked about that a little bit. The coin doesn't have a memory. It's not affected by previous ones. In our example, though, with the hearts, those were affected by previous ones. So it still works whether they're independent or not independent. Okay, so let's actually keep going here. So here's all the outcomes we could get. And so the probability of getting two heads, we would just use our formula and multiply those together. 1/2 times 1/2 is a 4. Okay, now that was two easy examples. Let's go through one that's a little bit more interesting. We're going to do a couple together, and then I'm going to pause and let you do one on your own, okay? Okay, so I'm going to read this. The Pew Internet and American Life Project finds that 93% of teenagers, which we're going to do 12 to 17, we're not including those 18 and 19-year-olds, use the internet, and that 55% of online teens have posted a profile on a social networking site. What percent of teens are online and have posted a profile? So now, first thing we want to do is figure out what are we asking here. If we're doing an and, this means we're doing the probability that they are online and that they've posted a profile on a social network, posted a profile, so profile. So what we want to do is try to figure out a tree diagram here. So what we're going to do is for the first branch, we're going to split it. What percent are online and which percent are not online? And then from there, we're going to split it again and say of those who are online, what percent are have posted and which have not. Now, this is what that tree diagram would look like. If 93% are online, what percent are not online? That would be 7%. Of those who are online, how many have posted to a social media, have a profile on social media? 55%, which means 45 have not. Now down here, of those who are not online, how many have posted to social media? Well, you can't. So it'd be obviously none of them have. So that's 100% go down here, 0 go up there. Now, if we're trying to figure out the probability that they are both online and have a social media, we would want to look at these two probabilities. This is a probability they're online. This is a probability they have a profile given they're online. So to do the and probability, we would just multiply those together. So the 0.93, that's just they're online. This probability they have a profile given they're online. So using our formula for the and, like if I were to go back, let me just go back real quick. This, if we want to do this formula, we have to have those two parts, which now we have. And so we can just multiply those together, and there we go. About 51% of teens are online and have posted a profile. Okay, let me show you just another example. When you read your book, you're going to see this one. This was just talking about adult internet users, what percent, different age groups, what percent of the different age group are online, and then what percent of them go to video sharing sites. And then you could use this to answer questions about, well, what's the probability of this and that? So if we're saying what's the probability that they are on videos and are on a certain age group, we're just going to be multiplying the 0.27 and the 0.7. So that's probability they're watching videos in that age group. This is a probability they're watching age groups in that older-ish. I'm not going to say older because I'm in that age group. And this is probability they're watching videos in that age group. And so if we wanted to find that they do watch videos, we would just basically add all three of those up. And there we go. All right. Those are three examples. What I want to do now is let you guys stop listening to me and try to do one on your own. Okay? So here's what we're talking about. This is called picking two sneezers. And what we mean by that are two people who have allergies, which means they sneeze a lot. Sneezing is so taboo in today's society. It's so crazy with this pandemic. It's like if you sneeze, someone's going to like do bad things to you. Anyway, suppose that we take 40 people from this like census website, and we're going to look at two variables. Are they male, and male or female, and do they have allergies? So what we're going to do is we're going to draw a tree diagram. And what I want you guys to do is I want you to try to make this tree diagram on your own, and then find the probability that the students are both oh, sorry, I think I said that wrong. So what we're going to do is we're going to look at two students. Suppose we choose two students at random. What we want to do is find the probability that both of them suffer from allergies. Now this one's a little bit tricky because we're not even worried about the gender on this one, okay? We're going to use that gender on a different example. But for this one, what I want you to do is practice drawing a tree diagram. Now, what you're going to be doing, though, is you're going to be looking at student 1 and student 2. So you're going to do the first branch based on student 1, and then you're going to do the second one based on student 2. And what the variable here is going to be is, do they have allergies? So based on student 1, did this person have allergies or not? And based off of that, the second student, randomly choosing them, we're not going to choose the same student, right? So it's going to change the probabilities just like it did here. So what I want you to do is take about a minute here, and I want you to see if you can figure out what percentages are going to go there, or even you can do the number of students. We don't have to do percentages here, but you can, okay? That's probably the better way. But try to fill it out, and then we'll go from there. So I'm going to give you 1 minute. So I'm going to set a timer for a minute. Go. All right. That was a minute. Edwin, I'm going to ask you to help me out on this one, okay? So
All right.
did you figure out what's the probabilities our first student, don't worry about gender, but just in general, what's the probability our first student has allergies?
18 over 40.
Awesome. So that would be 18 out of 40. So then what's the probability that they don't have allergies?
22 out of 40.
Great. So I'm going to write it like that. And I'm going to put NA for no allergies. So then if our first student does have allergies, what's the probability that our second student has allergies?
17 over 39.
Great. So then what's the probability that second student does not have allergies?
22 over 39.
Perfect. Nice job. So then let's go down to the other scenario where the first student didn't have allergies. What's the probability the second student did have allergies?
18 over 39.
And then what's the probability they didn't?
21 over 39.
Perfect. Nice job, Edwin. So
Thank
that's how you fill out this tree diagram. Now, part B says find the probability that both students suffer from allergies. We're going to use our formula. That means we want to find the probability that both student 1 has allergies and that student 2 has allergies. Well, according to our formula, we would just say, well, what's the probability student 1 has allergies? And then multiply it by the probability that student 2 has allergies, given that student 1 had allergies. Well, we found the probability of student 1 having allergies was 18 out of 40. And the probability that student 2 having allergies, given that student 1 did have allergies as well, was 17 out of 39. So I'm just going to go on my calculator and do 18 over 40 and times that by 17 over 39, and I get 0.196. Let's change that. So, and then I'd write a sentence summary. There is about a 20% chance that both students would suffer from allergies. All right, what do you guys think? Can you do stuff like that?
Yes.
Yep.
Yeah.
Yeah.
All right, I like it. Okay, now I'm going to give you another example here. And this one is going to be maybe a little closer to home. Maybe you have allergies, I don't know. But this one, for me, is all about students going on from high school to play at a college setting, okay? So if we're looking in high school, about 55% of high school students participate in a school athletic team at some level, okay? So about 55, so about half of high school kids play on some kind of sports team, okay? Whether it's varsity or JV. But of those athletes, only 5% go on to play at a college team in the NCAA. Kind of crazy. What percent of high school students play in a sport and go to this sport in the NCAA? I'm going to give you another minute here. What I want you to do is you're going to set up a tree diagram. Now, this tree diagram is only, it's for like our students in general. So what you're going to do is you're going to separate it by, in high school, do they play sports? And then in college, do they play sports? Now, to be fair, there are people who didn't play in college, in high school, but did play in college, and that information isn't provided. So we can't do the whole tree, but just try to figure out the top part of the tree, and then figure that out. And I'm going to give you a minute and come and see how you're doing, all right? Okay, 10-second warning. Okay, so I'm going to go to Rachel Shamo on this one. Rachel, how did you set up this tree diagram?
So I put 55% on high school and then 45% not.
Great.
And then I put 5% on
athletes going to colleges, and then 95% is not.
And we don't really know the other one, but it's asking us to find the probability that a student plays in high school and they play in college. So how would we figure that out?
So then you multiply 55% with 5%.
Awesome. That's using our formula there. So 0.55 times 0.05. Make sure you add that 0.05. That's going to make a big difference. And what did you get there, Rachel?
I didn't have a calculator on me, so I
That's
just
okay. I got you.
left it there.
So about 3% of students play both high school and college. Kind of crazy. But if I look at, like, for example, on my soccer team from last year, we had 2 kids going to college. And that was, and then like the year before, I don't know if we had any. So anyway, there's some variables in there. But that's how you would figure it out. Okay, do you have any questions? We're going to move on from this. This next one, it was interesting, but we don't really have time for it. Now, what I want to do here, I'm going to end this slideshow. I want to show you something. This, oh, sorry, it takes my screen like a minute to unpresent. I'm going to introduce you to your formula sheet. You can all see this, right? This is what you get to use on the AP test, this and a calculator. Now, when you go to probability and distributions, you only get 2 formulas here, okay? It gives you, this is your general addition rule, or sorry, this is probability of A or B. We got this last time. I think it's called the general addition rule. And then conditional probability, it looks like that. Now, this is where people are like freaking out. They're like, but it doesn't give us the formula for multiplication. Well, how can we get from this formula to the formula we just saw? We're just going to use some algebra here, okay? So let me show you what I mean. I'm going to copy that down, and I'm trying to memorize it. So what this formula said was a go to pen. So the probability of I forgot already. I got to go back. Don't stop. A given B is a probability of A and B over probability, and I think it was B, wasn't it? Yeah. Okay. Now, sometimes you'll need to know the conditional formula, and you've got it. But what if you wanted this equation? How could you algebraically solve for that equation? What would you need to do on both sides, guys? If you're dividing, what's the opposite of dividing?
Multiply.
Yeah, thank you. And look, this is the formula for A and B. And isn't that what we just saw? That's the general multiplication rule. So you don't have to memorize it, but you can remember, you can solve for it based off the formula sheet. So when you look at your formula sheet and it gives you one formula, well, really it's given you the other formula too. It's also given you the probability, it doesn't let me draw on this one, but the probability A and B is the probability of B times the probability of A given B, which that's what we just saw. So anyway, just pointing that out to you. Okay, we are going to do, this example is in your book, so I want you to read it. I'm going to do 2 that aren't in your book, and then we're going to call it good, okay? These are ones that I think are actually really interesting ones, and it's going to use our formula. It involves tree diagrams, and anyway, I think it's interesting. So we're going to do these 2 and then call it good. Okay, so let's read this first one. The Kaiser Family Foundation recently released a study about the influence of media in the lives of young people aged 8 to 18. In the study, 17% of the youth were classified as light users, 62% were classified as moderate users, and 21% were classified as heavy users, heavy media users. So how much time do you spend like around media? That could be online or TV or whatever, okay? Now, then they went through and looked at each group and they talked about their grades. Of the light users who responded, 74% described their grades as good, A's and B's, while only 68% of the moderate users were good grades and 52% of the heavy users were good grades. Suppose that we select one young person at random. What's the probability of A, B, and C? Okay, so now let's draw a tree diagram. Okay, so first off, what we're going to do is we're going to split it by their media usage, and then we're going to split it by the grades. Now this is going to have 3 branches, okay? Because in the media, they had the light, the moderate, and the heavy. So I'm going to say that's light, moderate, and heavy. It was given that the light, only 17% of them were in the light. In the moderate, it was 62%. And then heavy was 21. And that adds up to 100, so we are good there. Okay, now within each of those, either they were good grades or they were not. Okay, so for now, for the light media users, those that got good grades were 74%, so 0.74. I'm just going to do a smiley face for good grades, while the complement of that 0.26 were bad grades. In the moderate use, it says it went down to 68% were good grades, which the complement of that would be 0.32. So these are the good grades and these are the bad grades. And then lastly, for the heavy usage, we had 0.52 and 0.48. Good grades, bad grades. Okay, so now the first question, well, sorry, let me pause there. Does that make sense how you set that up? Do you have any questions on the setup? Assuming we're good, I didn't hear back from anyone, so we're good. Now we want to find the probability that we're randomly going to choose someone and that they have good grades. So what I want to do is I want to calculate the probability that we would choose someone that was either a light user that got good grade, a moderate user and got good grade, or a heavy user and got good grades. Okay, so what I'm going to do here is I'm going to go through and multiply these to give me all the different percentages, okay? So I'm going to get out my calculator and I'm going to do 0.17 times 0.74. And this percentage right here, the 0.1258, this is going to be the probability that they are a light user and they got good grade. But if I do the 0.17 times 0.26, I'm going to get 0.0442. That's a probability they were a light user with bad grades. Now I'll go to moderate user, 0.62 times 0.68. That's going to be that they were a moderate user with good grades, and that's 0.4216. And then that they were a moderate user with bad grades would be 0.62 times 0.32, which is 0.1984. All right, so now going down to the heavy users here. If we go to 0.21 times 0.52, that's going to be 0.1092. That would be the probability that they were a heavy user with good grades. But then the heavy users with bad grades is 0.21 times 0.48, and that's 0.1008. Now, you don't have to do this, but I'm going to hurry and add all of those together. And any guesses what we should get? Oh, 1, 2, 5. I didn't get, it was supposed to be 1, but it wasn't. So I think I pushed the wrong button. So I'm going to double check my work. There we go. I don't know if you can see my screen here. I have to go back to where I can even see me. But it's 1. You see, it added up to 1. All right, that means we did it right. Okay, now what this is asking is what's the probability that we randomly select someone and they got good grades? So of these, let's highlight which ones represent good grades. This was good grades, this was good grades, and this is good grades. So guess what we're going to do with those 3? We're going to add those up. So I do 0.1258 and 0.4216 and 0.1092. When I do, I get 0.6566. That would be the probability we randomly select someone and they got good grades.
Genius.
Yes. Now, I guess the real question is does that make sense? Do you have any questions before I go to C? All right, so now on part C, it says, given that this person describes his or her grades as good, what is the probability that he or she is a heavy user of media? Okay, so what we're asking here is we're trying to find the probability that they are, it says, given that they have good grades, what's the probability that they're a heavy user of media? So what I want to do is I want to write this out in probability notation first. Okay, so this is what's the probability that they're a heavy user given that they have good grades? So for example, we go up to someone, we randomly choose someone, they say, well, I got good grades. Well, what's the probability that then they're going to be in our heavy media usage, right? Let's read that and make sure we're all on the same page. Given that this person describes his or her grades as good, what is the probability that he or she is a heavy media user? Okay, we'll look back at our formula sheet. How do we calculate conditional probability? This would be the probability of A and B over the probability of B. What that means is that we're going to look at the probability that they are a heavy media user and they got good grades. And then we're going to divide that by the probability that they got good grades. Checking my formula to make sure I did that right, but I'm feeling good about that. Yes. Okay, now here's the good news is you've already done all the calculations to figure that out. What's the probability that they are a heavy media user and they got good grades? That's this guy right here. Now, what's the probability that they got good grades? That's this 0.6566. That was what we figured out in part B, that was probability they got good grades. We just looked at all of them and so I'm going to show that right here. That's this one. That goes right there. So to figure this out, I'm going to take the 0.1092 and we're going to divide it by the 0.6566. And I get a 0.16. So what that means is that if we randomly choose someone, but we know that they got good grades, then there's about a 16% chance that that person was a heavy media usage person. All right. That's how you use the formulas. That's how you do the tree diagrams. And that's about where we're going to pause it for today. What I'm going to ask you guys to do, okay, is I want you to try to work through this false positive and drug testing one. I'm going to go through it separately and post it later, but I want you guys to try to do it on your own and see if you can figure it out. It's going to be doing the same thing of what we do here, but it's going to be a different context. And I think this is a really interesting one too. And then next time we're going to finish that. So let me stop sharing with you so I can look at you. And this is where you guys are going to unmute your camera so I can see you. So we unmute you if you're okay with that. Yay, there's Jordan. Okay, thanks, Casey. So what we're going to be doing, guys, you've got a couple things. Number one, 5.2 quiz is on Canvas. You need to do the 5.2 quiz. Cool? Thumbs up? 5.2 quiz. Great. Then you need to start doing the 5.3. The homework's a little tricky because we've only covered half the material, so there's a chance the questions you might not know how to do those yet, and that's okay. But start reading through it. Do the homework questions you can. But then also I want you to go and do that drug testing example that I just left off on. Even right now, because I'm going to end like a half hour early, you guys can try that out. And then I'll post a video later and email it to you so you can check your work, okay? Do you have any questions before I let you go? If so, now's the time to speak. If you want, you can wait until people leave and then I can talk to you from there. But thank you guys for tuning in. I hope this is helpful. I know it's not ideal, but I hope you're getting the idea of it. We're going to do one more on 5.3 and then we're going to review and test. Before you leave though, do you know the updated schedule for next week? So today is
No.
it's Thursday. Friday is a B day, but then Monday is another B day. So it goes 2 B days in a row, and that means the next time we have class is going to be next Tuesday as an A day. And it's going to be a distance learning day because we only have school for 2 days and they don't ask us to do the Zoom meetings on Tuesday. So I'll just record a video and post it for you. So from today, I'm going to see you guys next on Tuesday, and it's going to be a distance learning day. Does that make sense?
Monday's a B day.
Yes, so Monday is a B day. They changed it because they didn't want to have B day be 2 distance learning days in a row. That was before we were on distance learning closure. So in the end, it didn't make too big of a difference, but whatever. So I will see you guys. I'll give you an update on Tuesday. But if you have any questions, please reach out to me. We can do email or Zoom, okay? All right, cool.
Okay.
Well, thanks, guys. Appreciate it. I will be talking soon.
Okay. Thank you.
See you, Sober.
Thank you, everyone.
Yeah. Peace.
The 30th is an A day. So then it will go back to being A day. Cool. Thanks, Lillian. Oh, where is it?